I will do logic synthesis with Verilog HDL. Verilog, Verilog HDL synthesis we are doing here. Session 6. This Verilog constructs. What are construct it is allowed in our logic synthesis and which are not allowed in the logic synthesis. That tunnel we will discuss here. Here for the purpose of logic synthesis, design are currently written in an HDL at a register transfer level. Logic synthesis is tools take the register transfer level HDL description and convert it to an optimized gate level netlist. And here, Verilog and VHDL are the two most popular HDLs we are using for the logic synthesis. And here some of the constructs type and keywords listed here which are allowed in the logic synthesis and which are not allowed also it is given in this. Here the not all the constructs can be used when writing a description for a logic synthesis tool. The list of constructs that are typically accepted by logic synthesis tool here are construction type in this column and keywords and nodes. What are the it is taking place? All those things it is given in this nodes. On ports, input, in-out, output ports. These are used as a input and output signals. And in-out is for the both input and output when some signals we are going to use for the input and as well as output for that we are going to use. For example, buffer. Buffer we are using as a in-out. And parameters, some constants we want to declare, then we are going to use a parameters. And module definition, the keyword is module and signals variables are wire, register, try. These are the signals and variables that is in this vectors are allowed. Then in this wire register vectors are allowed. Instantiation in this we're going to use a model instance, primitive gate instances. For the instantiation we are using a model instance and primitive gate instances. Here, the MyMux M1, M1 is an instance name, and MyMux is a source code that is which is written by model instance. That is when you are written a model my definition MyMux that is actually source code and M1 is a instance. That these are the input output list of signals, and here registers and wires we're going to take here. And NAND is a primitive instance we are using. And function and task. For that, we're going to use the keywords function and task. Here, timing constructs are ignored. In this, timing constructs are ignored. And procedural constructs is always if, then, else, case X, case Z. These are the keywords we are using, and initial is not supported. Initial is not supported. Always if, then, else, case X, Z are allowed. Here timing construct that is using hash delay. All those things we cannot use in a function and task timing construct because it is mismatches the input and output when you do the logic synthesis. For that we will going to ignore this. And procedural blocks begin, end, disable. Begin, end, disable, that is begin and end for the procedural blocks. And when you are using a named procedural blocks, then we have to disable that. For that we're going to use a keyword disable for disabling the named blocks. Named blocks it is allowed disable. And data flow, that is assign keyword we are using. Here delay information is ignored. We are not considering the delay information in the logic synthesis. And for loop, while loop, forever loop. In the for loop, we are having we are not cannot use the positives and negatives, so it automatically will going to have a conditional to terminate that we are going to use a conditional operation in the middle of this, so that it is here posits is not considered. Here we must have to use in forever and while loop. We must have to use a posits clock and negative clock. It is used in the while and forever loops. Must contain that. And here, some list constructs that are typical not accepted by logic synthesis tool. That is, while and forever loops must be broken up by at positive clock and negative clock statement to enforce that cycle by cycle behavior and to prevent the combinational feedback. Combinational feedback. For that, we need to use broken up by a positive clock or negative clock. And logic synthesis ignores all timing delays specified by hash delay construct. Therefore, pre and post synthesis Verilog simulation results may not match. Pre-synthesis and post-synthesis Verilog simulation results may not match in this. Because of this, hash delay is not allowed in this logic synthesis. It is ignored. And initial construct is not supported by logic synthesis tools. Instead, the designer must use a reset mechanism to initialize the signals in the circuit. Initial construct is not supported by logic synthesis tools. Instead, the designer must use reset mechanism to initialize the signals in the circuit. Okay, this is the about some constructs which are given in this logic synthesis. Some operators, almost all operators are allowed in uh, Verilog for the logic synthesis. Here, arithmetic operators, all arithmetic operators, that is multiply, divide, add, subtract, modulus, unary plus, unary minus. These are the operators. Or priority wise also it is listed here. And highest priority is multiplication, that is listed here. And logical operators, negation operation, AND operation, OR operation, all the things are here. And here relational operation greater than or equal to less than or equal to are the relational operators and reduction operators. And this is a bitwise reduction operation. It is a reduction and not NAND, reduction NAND, and reduction R, reduction NAR, reduction XR, reduction XNAR. Same operators can be used for the bitwise operation also. See, that is only here we are having, that is negation, bitwise and bitwise R, bitwise XR, bitwise XNAR operator. Bitwise reduction of NAR operation is also same thing, as well as bitwise XNAR also is same operator, and XR also. XR R operation, same thing, and that we are going to use for this. These are the bitwise operators, but there is no NAND, bitwise NAND and bitwise and NAND and NAR are not there in this. And shift operators, that is double greater than symbols are there. Right shift operation, double less than shifts, it is a left shift operator, and three greater than symbols are arithmetic right shift and arithmetic left shift. Here arithmetic left shift is for two less than, three less than symbols, and three greater than symbols for the arithmetic right shift operators. And concatenation operation, here we are having a two curly braces concatenation. When you wanted to place some variables one after the other, then we are going to use a concatenation operation. And conditional operation is a question mark colon, is a conditional operation. Equality operator is here, that is double equal, not equal, inequality is a not equal operator. And only operators such as triple equal and not triple, these are the these that are not allowed in the logic synthesis, because that are related to x, the unknown and high impedance are not allowed. because equality with x and z does not have a much match meaning in a logic synthesis. For that purpose, it is not allowed in a logic synthesis. Okay, and interpretation of few Verloc constructs. Some constructs are interpreting here. That is to understand how logic synthesis tools frequently interpret these constructs and translate them to logic gates. That is discussed here. Uh, the assign statement. The assigned construct is the most fundamental construct used to describe combinational logic at an RTL level. Given below is a logic expression that uses the assign statement and that is assign out is equal to A and B we are using. That is with an example here. Assign out is equal to A and B. It is here. See here, it is going to interpret. It is suppose if you are having a and B are the two bits, then it will assign to CL. It is going to take a out, that is suppose A, B, C are out are the two bit vectors, then that is you assign to the two bits A of 0 and A of 1 also. That is assign statement, and one bit full adder is implemented. One bit full adder also you can implement using this assign statement, that is by concatenation operation. That is A plus B plus C in, that is C out comma sum implemented. And the conditional operator also we can use to multiplexer circuit is in fact here. That is here multiplexer gate level represent frequently frequently translate to the gate level this thing, multiplexer. Here we are using if else statement. One bit multiplexer can be easily developed, but if you are using a if else statement, it is for more number of bit n number of bit mux generate to develop that, it is not possible in this case of if else statement. That is how we are using here. If selector is there means we are going to use out is equal to I of 1, out is equal to 0, I 0 we are using else. And in case statement it is allows all those case 1 bit 0 out is equal to 0, and that is allowed here. And for in the for loops also it interpret here. You can for loops can be used to build a cascaded combinational logic. For example, 8-bit full adder can be developed by using this statement. For I is equal to 0 to I less than or equal to 7. That is concatenation of sum of I, C comma compared sum of I. That is A of I plus B of I plus C. So that addition can be assigned to this. Then it will give you that result here. And C out here we are giving a C in first input to the C, and next it will be it will adding that C values, and then out C out is again we are giving this thing, this simple operation. All of you know that when you are generating a 4-bit to 3-bit full adder, ripple carry adder, we have done. And the same thing, same operation here also we are doing. And using always statements, we can use we infer sequential and combinational logic. We can statement can be used to infer sequential and combinational logic. That is always at posits of clock. Q is equal to D. Q is assigned to D. That is it's triggered D flip flop we are doing, and also that is by using a that is event that is sensitive list. Also we can use here. AR, BR, C in at the any signal changes, we can assign that value to the adder circuit. That is C out commas the sum A plus B plus C in. Always statement can be inferred this. This is a sequential logic. This is combinational logic. For that we are using here. See, always statement can be used to infer sequential combinational logic. For sequential logic, the always statement must be controlled by the change in the value of clock signal. Clock and see here we are using a that is edge triggered D flip flop as D and D as input and Q as output. Clock V as the clocking signal. At the posits of clock Q is equal to D we are doing. And see it is also level sensitive latch also we can use clock or D. That level sensitive we are doing here. If clock changes, Q is assigned with the value of D. That is level sensitive. Latch also we have developed here. And that is using this sequential logics. It is allowed in this. And for combinational logic, already I told, we are using that is here order circuit. Combinational logic, the always statement must be triggered by a signal other than the clock's reset and preset. For example, the clock block will be interpreted as a 1-bit full adder. Here it is. Yeah, we are seeing it is a level sensitive list, and that is whenever the A, B, C changes, that will be added here. Arithmetic operation takes place, and it will be assigned to the sum. And if carry is there, means it will comes to the C out. Okay, this is the uh, for loop. And function statement. See, function synthesized to combinational blocks with one output variable. That is here. Function, where declare definition is this one. Function declaration. 4 down to 0 will add input 3 down to 0. A comma B input C in begin full adder. We are calling that full adder. This is a function we are calling with a value that is 4-bit values we are assigning A plus B plus C in end function. See here 4-bit of full adder for carry bits 3 down to 0 for sum we are assigning. We are calling here full add and sending the signals here. So this is the session 6 and I referred the book Verlag HDL, A Guide to Digital Design and Synthesis by Samir Panitkar, forwarded by Prabhu Goyal. And this is our LMS team for Verlag HDL. Dr. Rangaraju sir, he is from GSK SGSTI, Bangalore, Chairman LMS courses, and Professor Rekha RS, HOD of EC Department, GC Chamarajanagar. Dr. Rudrappa KM, he is from JC Carpenter, he is HOD in EC Department. He is our moderator, LMS Verlag HDL moderator, and myself, Leelavati VV, Assistant Professor, GC Chamarajanagar. I am a content developer. Okay, thank you.